Hello, welcome to our webinar today. Our topic is key skills for acceptance sampling. It's brought to you by ASQ Statistics Division and the ASQ Audit Division. Our speaker today is Karen Holting. Couple of housekeeping items. Everybody's going to be muted today, so if you have questions throughout the presentation, you can type them into the chat and we will, we will read your questions at the end of the presentation. If you have any technical difficulties, you can type those into the chat as well, and I will help you as much as I can with any technical issues you have. After the presentation and in the next couple of days, you'll get an email that has a record of your RUs for watching the webinar. I'll also give you a link for the YouTube channel where the recording will be posted, and also a link for where you can find the presentation slides. So I'll have all that, and I may post those links in the chat for you as well. So our speaker today again is Karen Holting, who is a statistician, coach, and teacher. She has over 30 years of experience in the medical device and automotive industries, where she has applied a broad range of statistical methods in manufacturing, research and development, and quality. She has a master's and PhD in statistics from the Iowa State University and an undergraduate degree in mathematics from St. Olaf College. She's a fellow in ASQ and an adjunct instructor at St. Cloud State University graduate program in medical technology quality in Plymouth, Minnesota. And with that, I'm going to turn it over to Karen. And I know this is a great talk because I heard it before at the joint, oh, now I'm going to not be able to say it right.
World Conference on Quality and Improvement.
Thank you.
WCQI.
Okay.
Just this past
Thanks,
Friday.
Karen.
Oh, you're welcome, Jenny. Thanks so much I'm just delighted to be here today. So our topic today is key skills for acceptance sampling. Of course, the topic, you can get whole books on this. So what we're going to try to do today is kind of hit the high points to help you be, whatever state you're at right now in acceptance sampling. I hope you know something new by the end of this hour. So let's see, I gotta get there we go. Okay, so what we're going to try to do today is talk about all these terms and acronyms and lots of the words that are used in acceptance sampling. And we're going to talk about, more, I would say more than any topic that I sort of help people with in these risky industries I've been in, right? I've been in medical device and automotive, a little bit of pharma in combination devices. I work for Medtronic. And in those kinds of industries that have some risk, we end up needing to use acceptance sampling. And I would say of all the tools that we use, it's the one that's got the most misconceptions that make it difficult to use. So hopefully we'll kind of talk about some of those things that we think are true that aren't actually true, and then what is really true about it and how to use it well. There are particular applications of acceptance sampling that are really appropriate. There are some uses of acceptance sampling that are not. So we'll talk about both of those. Now, there's this term, strong statistical rationale. So we're going to talk about how do we plan an acceptance sampling strategy that has strong statistical rationale, and what is that? What is statistical rationale? And then I'm going to show you how to implement this. So whether you've got commercial software, a lot of commercial software packages will help you get an OC curve. That's what we're going to be talking about. And if you don't have those commercial packages, you can actually do this in any spreadsheet program. So even Google Sheets will allow you to do, not for every complicated acceptance sampling plan, but for the acceptance sampling plans that get used the most, all you need is a spreadsheet. So we'll talk about that. Like Jenny said, if you have questions, certainly type them into the chat. She's going to be monitoring the chat, and then we'll talk through all the questions at the end. And again, like she said, if you have any technical issues or, if something's going wrong, let her know and she can help you with that. Okay, so start with definitions. So an acceptance sampling plan just means that we want to make a decision about a population. Typically, that population is a lot of product that has been produced. And we need to make a decision about that lot. The two decisions are we're going to ship it or we're going to hold it, right? It's either a pass or a fail. Now that occurs Where we think about this the most, we think about this in manufacturing, accept or hold a lot of manufactured product. It also applies to things like process validation, where we're making a decision about that process based on a sample of data, or design verification. And these are terms that I'm used to using in medical device. You might use slightly different terms, but if you're trying to make a decision about a product design, and you make a sample of that product, and then make a decision about whether that product is good enough to go forward. And so we tend to use the language of acceptance sampling mostly in manufacturing, and we tend to sometimes use other language for the same kinds of probabilities when we're using sample plans in other contexts, but this language can apply to any of those cases. And so I tell people, acceptance sampling, what it's really good at is protecting both producers and consumers from the release of highly defective lots, right? If things have all of a sudden gone badly, acceptance sampling is our insurance policy to find out. In that statement, it doesn't say that acceptance sampling is going to guard us against any decrease in quality. It's not very good at alerting us when a very small change has happened. It's really good at alerting us when a big change has happened. Now, we hope big changes don't happen, right? We hope that we don't have big surprises, but in risky industries, it's great to have this insurance policy. Now, the reason that I call it a key skill is that it is a huge confidence booster when folks who need to use this methodology, either, especially in this webinar, we're talking about folks who would use this as auditors and folks who would use this in an audit, right? That conversation, I find that the more both people on either side of that conversation in an audit understand this terminology and understand where the terminology can be confusing, it's very helpful. So you're going to be a great value to your organization the more you understand about this technology of an operating characteristic curve or acceptance sampling. Okay, so we're going to start out with a couple really important distinctions about acceptance sampling plans. And there are more distinctions, that as you get deeper into this topic, you might learn about. But the two most important are, what kind of data do we have that we're going to make this decision on? So we can have either attribute or variables data. The most typical attribute data is pass-fail data. And so acceptance sampling plans using pass-fail data are very, very common. I would say they're the most commonly used acceptance sampling plans. In that case, all you need to do to specify your acceptance sampling plan is know a sample size N and an acceptance number. Usually that's denoted by C, a lowercase c, sometimes a lowercase a. And that's the total number of defectives in that sample that you can observe and still make the decision to release that lot. Sometimes that number, very often that number is 0, right? We do accept on 0 acceptance sampling plans, but sometimes that acceptance number can be 1 or 2 or 3 or 4, depending on the sample size, it could be even higher than that. The other kind of acceptance sampling plan is a variables acceptance sampling plan, where we take variables data, right? We make measurements, dimensions, strengths, all kinds of things that are variables data, calculate the mean and the standard deviation, and feed that into a formula that tells us whether or not we accept or reject that lot. Variables acceptance sampling plans are really, really powerful, but they're a little trickier to implement. So we'll talk a little bit about that. The other so first you need to know what kind of data you have. Then you can decide to use what's called a single sampling plan, where you take one sample and make a decision. You can also do what's called multiple sampling. The most common of those is a double sampling plan, where sometimes whenever you do a double sampling plan, you plan ahead for the possibility of taking a second sample if the first sample is not conclusive, right? Sometimes, in a single sampling plan, you just have to draw a line and say pass or fail. In a double sampling plan, you can have really good levels of quality where you pass, really bad levels of quality where you fail, just based on the first sample. And in the middle, you have this possibility of taking a second sample to make a more precise decision. Now, the important thing about a double sampling plan is it is intended and only actually works if you plan ahead for that second sample. It doesn't work if you failed the first sample and then you say, let's do a double plan, right? If you do that, first of all, that is a misuse of that double sampling plan. And second of all, it increases your risk, right? So it's not a good idea. But you can plan ahead for a double sampling plan. And so in some cases, that's a really good method. Okay, now this I would say is probably, this is a very important slide in this whole presentation because kind of everything that we're going to be talking about is illustrated in this one slide. So I have kind of a cartoonish version of an OC curve over here on the side of this slide. And you'll notice folks who've used Minitab might recognize the look of this graph. It comes from Minitab. I'm going to show you later how to get a very similar graph out of Google Sheets or Excel. But this is kind of my illustration of an operating characteristic curve. And you'll notice it's kind of an odd sample plan that it's illustrating. It's a sample size, it's an attribute plan, single sampling, sample size of 38, except on 4. Now, for folks who've used acceptance sampling, that's a very unusual plan. I don't think I've ever used it. The reason that it's in the illustration here is because it allows me to point things out in that curve. We'll see some other OC curves very shortly where it's a little hard to tell where does that curve start dropping down from 1 down to 0 and where does it flatten out. This curve, we can really see that. And so we can kind of see a point at the top where it's a little bit flat and the point, let's see if I can use, maybe you can see let's see. We'll just grab my laser pointer. So it's kind of up in this area where it's kind of flat at the top and down this area where it's flat at the bottom. So the important thing about this curve is it's simply an XY curve. The x-axis is the lot percent defective. Now this is the true value, the percent defective in the lot we're trying to decide. Now typically we don't know what that is. And so we use that x-axis as a what if, right? What if the percent defective in my lot was 10%, right? Sitting right here, this kind of tells us what if my lot had 10% defective, how would my acceptance sampling plan work? And so you don't need to know this value in order for this curve to be very, very useful. Now, the y-axis, that is the probability that you will accept in this acceptance sampling plan. So the probability that your outcome is yes, ship that product. And so that's just a probability calculation that uses as its input that percent defective. And so we'll talk in the next slide about how those calculations are done. But this is just the probability of acceptance from 0 to 1. And so not surprisingly, we find that when we have 0% defective in the lot, then the probability of accepting that lot is 1.0, right? There's no defectives to find. And so we are definitely going to ship that lot. It's 1.0. As that lot percent defective gets higher, we have less and less chance of accepting that lot down to where we get to a point where there's essentially 0 chance if we've got a highly defective lot. In the middle, here's the tricky thing about acceptance sampling. In the middle, there is at one point, there's a 50-50 chance of passing or failing that lot for a level of defective, that's not 0, right? So, in this case, if we go to the 50-50 point, it's somewhere above 10%. So if I had it for this sampling plan, if I had a lot that I didn't know it, but it was, 15% defective, then it's almost like flipping coins, whether or not that lot gets out the door. Okay, so let's talk about all of this language over here, all the formulas and that sort of thing that are illustrated with this slide. So first we're going to talk, the whole thing is called an operating characteristic curve because it tells us what's going to happen when we use this acceptance sampling plan. The next two values here are alpha and beta, and so those are risk probabilities. And so alpha is called the producer's risk because it is the chance that the producer gets the outcome they don't like, meaning the producer has produced a lot that they feel to be of adequate quality and it still fails the acceptance sampling. And so that value is, that probability is alpha. And where it shows up on our graph is as 1 minus alpha, or actually the probability that that good quality is accepted. And so we sort of point out here, if alpha is 0.05, then 1 minus alpha is 0.95. And we kind of draw a line across this graph. And we discover that at this point where the OC curve is sitting at 0.95, if we go down to the lot percent defective, that is a very important value on this graph. It's actually the definition of the AQL, or acceptable quality level. And so that alpha value determines what the AQL is, and the AQL is just the value on the x-axis where that OC curve has dropped to 1 minus alpha. And so the idea is that that is, we'd love to always produce perfect product, right? We'd like there to be no defectives in the lot, but we define that value as the good quality that typically will be accepted by the acceptance sampling plan. And so then you can find out for this acceptance sampling plan, what kind of quality typically gets accepted. And so that's important to know. There's another probability value, this beta, that's called the consumer's risk, because that's the probability that the person buying this product has that product shipped to them when the quality might not be as high as we'd like to have it. And so we set beta as, and interestingly, these two probability values, in typical practice, they're different. we typically set the beta value to 10% and the alpha value to 5%. Now, you absolutely can use beta values of 5%, right? And sometimes, different companies will use these tools in different ways. It is a perfectly fine practice to change that beta value to 5%. It just means that you need to keep track of that because it's a different point on the OC curve. What we're illustrating here is with a beta of 10%, we go across, and where that line intersects the OC curve, that percent defective is called the lot tolerance percent defective. And so that is, that's the bad quality level that the acceptance sampling plan will typically detect, right? So that's really important. We kind of talk about that as the consumer's risk, but we're going to talk about later that I find that value is as much a producer risk as a consumer risk when you're dealing with risky products. So the LTPD, sometimes called rejectable quality level, RQL. So those two acronyms are meaning exactly the same thing. This LTPD language is more historical, right? It's been used for longer. The RQL language was invented more recently to kind of be parallel to the AQL language. But LTPD or RQL is trying to say what bad quality will the acceptance plan detect, and the AQL is asking what good quality, supposed good but imperfect quality, will the acceptance sampling plan typically accept. Okay. So when you get the PDF of this, you may find that that's the slide you go back to really know what that AQL is defined as. Now, how are these probabilities calculated? Just with typical probability calculations. So if you've got an attribute plan with pass-fail data, then we're using binomial calculations for that. And if you've got an acceptance sampling plan with variables data, typically using normal distribution probabilities. Now, we all know that not all variables data follows a normal distribution. So when you're using variables acceptance sampling plans, topics like transformations and other more advanced topics do come into that conversation. That's really why attribute acceptance sampling plans get a lot of use because you don't have to worry about distribution fit and that sort of thing. But they take bigger sample sizes and are not quite as powerful. So both are really good acceptance sampling plans. But this is the basis. And because these probability calculations are very standard, that's why you can use spreadsheet tools to do some of these OC curve calculations. Okay. So let's look at some very typical attribute single sampling plans. I would say, you know, I can really only speak for the industry that I've been in most recently for a long time, and that's medical device. The medical device industry really likes accept on zero plans. And so this illustration here shows you 4 different attributes, single sampling plans. They all have acceptance numbers of 0. They just have different sample sizes. And so we'll see how those sample sizes affect the OC curves. The two things that, the 2 reasons that people like accept on zero plans is they have the, for a given situation, they have the smallest, they have small sample, we'll just say they have small sample sizes, and they have the advantage that you haven't detected the kind of difficult thing of detecting a defect and still shipping the product, right? We're uncomfortable still shipping product if we've found any defects at all. And so this allows us to only ship when we found no defects at all. Now, the logical problem with that is that just because we saw no defects, especially if we have a small sample size, that doesn't mean there are none in the product, right? It just means we haven't seen them. And so sometimes people are more comfortable than they should be with small sample sizes and accept on zero plans. So let's take a look now at, for these plans, what are the AQLs and what are the RQLs or LTPDs? And so these accept on zero plans, the OC curve drops really fast. And so that's why I don't use them in my illustration of the OC curve, because you really can't even see the point where that OC curve is kind of flat at the top, because it really just drops. Accept on zero plans are not very forgiving on any defects at all, not surprisingly. So the probability of acceptance drops very fast, even with the smallest sample size. You can see this solid blue line here, that probability drops very fast. It's dropped all the way down to 50% by, you know, about 3% defective in that lot. So if you look at that x-axis here. The bigger the sample size, the faster it drops, because you have more probability of getting a defective for any level of defectives in that lot. But, you know, we draw our line across here at 95%, and so you almost can't see any difference between the AQLs, but they're kind of sitting there right around 1% for all of these acceptance sampling plans that I'm illustrating on this slide. The AQL, the point where the acceptance or the OC curve has gotten down to 95%. We just run that down to this axis and we see it's about 1%. Now the RQL is what's so different. The smallest sample has an RQL out here, closing in on 8%, it's probably 7 point something. As the sample size gets larger, then that RQL gets smaller, which means those larger sample sizes are more protective. Right? You don't have to get to as high a percent defective before you have a really good chance of holding that product. And so this is probably the more common application of an OC curve. But I think it's, as we'll talk about later, you often use the term AQL sampling, and it's really good to understand what really is the AQL of a sample plan. You can read it right off the OC curve. So now we're going to go through a few misconceptions, then we're going to talk about how to deal with those misconceptions. So the first one is that lot size is a big deal in acceptance sampling. And it turns out that the lot size, you know, how big of a lot, did I produce a lot of 100 units, or did I produce a lot of 1,000 or 10,000? Those lot sizes don't matter very much to the OC curve. Right? They matter in other ways that I'm going to talk about, but they don't matter to the OC curve, so they don't matter very much to the AQL or the RQL. It has a minimal effect, and folks who are have used this technology more, you'll know that there are a couple different ways to do the calculations. And so that little adjustment makes it'll shift the OC curve just a very small amount. And you can run those calculations in some of the software programs, and you can see that it doesn't change the OC curve very much. It turns out that all you need to know for the OC curve is what's the sample size and the acceptance criterion, not what the lot size was. Now, here's why we have this misconception, is because the sampling standards devised, or the tables that we use to use acceptance sampling plans, are indexed by lot size. And the reason for that is the folks who invented those sampling standards wanted stronger protection for bigger lots. So that's why they're indexed by lot size, because when you're buying more, you want a bigger sample size so that you can have more protection against bad quality. It's also easier to have a big sample size in a big lot, right? Because you are sacrificing a smaller percent of the sample. And so the OC curve actually doesn't care very much about lot size, but the sampling standards were set up to make it look like the lot size was a big consideration in the OC curve. Second misperception, that AQL is the most important thing. Now, the way that this arose in my work life is oftentimes I'd hear people talking about, we're going to do AQL sampling. And if we're in a risky industry, the really important thing is we care much more about the LTPD or the RQL, right? That if we're in a risky industry, even as a producer, I want to know how bad does this product have to get before I have a high chance of catching it, right? I want to know what levels of bad quality may I be unaware of, right? May I be blind? There's that range in the middle of the OC curve where I wouldn't even know that the quality was bad and it still gets shipped. I want to know about that. So the LTPD is much more concerned to me. I want to know the AQL. It's important, but it's not the most important thing in doing an acceptance sampling plan. Now, sampling standards are indexed by AQL because they were invented for the use of producers, right? The producers wanted to put in an acceptance sampling plan, and the producers are concerned that the level of quality that they consider to be acceptable, that mostly gets shipped. Now, that is kind of a logical struggle, especially in a risky industry. We don't want to accept any level of nonconformance, right? So we're going to talk about how we can handle that in a plan with statistical rationale. But I would just say the most important takeaway from this slide is that industries with high risk ought to be focusing primarily on LTPD as a first concern, and then look at AQL as a second concern. And I'll show you how to do that. And then the third misconception, and I would say this is much, much less common than it used to be maybe 20, 30 years ago, is that acceptance sampling provides adequate process control. It just doesn't. And so many, many years ago, it was pointed out that acceptance sampling is reactive. All it does is check the quality after product is produced. It is not enough, because we've noticed that, it still allows some level of defects to get through. And so what we want to do is view acceptance sampling as a really important tool to prevent highly defective lots, the ones that are out by the LTPD. It prevents those lots from getting out the door, or those processes from being accepted. But we need to use, increased process understanding, DMAIC programs, all kinds of proactive tools, and good process control, using SPC and all these kinds of things to actually do adequate process control. And that's really why acceptance sampling got a bad name, because occasionally it was being used as the only process control, and it's just not good for that. Okay, so what are appropriate uses? I think I've mentioned this a little bit already. It is an insurance policy against the release or acceptance of highly defective lots. It's good to use acceptance sampling in tandem with these more proactive tools. If you can take your sample, get the sample data, and not only make an acceptance sampling decision with that sample, but then use that data in a control chart, right? You could use it in a P chart. If it's variables data, you could use it in an XBAR R chart, XBAR S chart. And so then you can get double use of that tool and, use that data proactively as well to be able to see, is that process trending? Is something getting worse gradually? Or did we suddenly get a process upset? So these are the appropriate uses, and it's really important to know that it is an insurance policy against the acceptance of highly defective lots. Okay. So the other thing that we really want to deliver in this presentation is, how do you choose an acceptance sampling plan? So this is helpful for both the folks who are choosing the plans. It's also helpful for the folks who need to defend an acceptance sampling plan in an audit, or for an auditor who wants to ask questions about whether the acceptance sampling plans that are in use are adequate for the use they're having for them. Just one second. Okay, so it's the OC curve that's going to help us choose an acceptance sampling plan that has statistical rationale. And so we're going to go back to that idea that the AQL tells us what good quality we want to mostly accept. The RQL tells us what bad level of quality do we mostly want to reject. Step one is always going to be risk assessment. We need to understand what risks are we taking on with this product. And so even if you're working in a manufacturing facility, you need to have a way to interact with your team members that can help you understand, in a medical device, what are the clinical implications of a defective unit getting out of the factory, right? You need to know what happens if a defective gets out of the factory. So step one, assess risk. Hopefully you have a procedure with which to do that. Typically that means putting this product into a category of risk. Maybe you have 5 categories, maybe 3 categories, maybe 10 categories, but you want to have a procedure for making that risk determination. Then ideally you would have a procedure that takes all of your risk levels and has a little table that says, what's the LTPD for each of those risk levels? Now, that little table is often a hot potato, right? Nobody wants to be the one that says, for each of these risk levels, how much risk can we accept? Because we want to accept no risk, right? But we have to decide in this industry, say we had 3 risk levels for a simple situation, then you need to decide what are the LTPDs or RQLs that are okay for that level of risk. The LTPD is going to be lower for higher risk, right? The higher the risk, the lower the LTPD. And so you just need to set LTPD levels that make sense for your industry and your levels of risk. And if you've got those 2 documents, you've got a risk assessment procedure, and you have somewhere, there's a little table, maybe it's in the risk assessment procedure, maybe it's in a statistics procedure, maybe it's in a process control procedure. Somewhere you need to find this little table that tells you for each of the levels of risk, what have we decided is an appropriate LTPD or RQL. Now it might be different for different product lines, right? You might have more risky and less risky product lines. They might have a different table. Okay, then once you know what the RQL is, say that your RQL has to be 10%, right? Or 5%, some value of lot percent effective that you want to catch. Then you can identify sample plans that meet that RQL. There's going to be accept on 0 sample plans. There's going to be, accept on 1, 2, 3, 4 attribute acceptance sampling plans. There's going to be variables acceptance sampling plans. There's going to be single and double plans, right? There's going to be a whole menu of potential acceptance sampling plans. That's what you're going to need the bigger book for, because we're not going to go through how to determine which of those kinds of plans to use. We're talking here more about, once you've got an acceptance sampling plan, how do you assess it with an OC curve? But there, that third step there, sometimes different facilities will use only attribute accept on 0 plans, and then there's only going to be one that meets, that is the smallest sample size that meets your RQL, right? So that does simplify it, but sometimes it's good to have some options. Now, then the 4th step is, once you've decided on maybe a set of different plans that meet the RQL or LTPD that you need for your level of risk, then you can look at all of those plans, see what their AQLs are, and choose one that has an AQL that matches your current good performance. So you need to know what percent effective is your process currently running, right? Is it running 0.5%, 0.1%, 2%, right? What percent defective do you consider to be tolerable for your, this is both an economic and a safety decision, right? What is a level of defectives in your production stream? And it is logically difficult, right? It's difficult to say that we accept anything other than perfection. But perfection doesn't exist all that often. Okay, so there's the method of getting, a plan has statistical rationale if it has that risk assessment, and then you have matched the risk with the right level of alphas and betas, the protection that you are provided. And so this is a prescription for having statistical rationale in your sampling plan. Now, you will recognize, these slides right here are not giving you usable versions of these tables, but probably anyone who's worked in acceptance sampling, this kind of table will be familiar. These are the ANSI ASQ attribute sampling standards. And so, like we were saying before, you start out with what is the lot or batch size, and that is your entry into these sampling standards. You use that, and then you have to decide what inspection level. This one gives you 7 possibilities. That gives you a letter that you then use as your entry into the actual sample size table. And so what's going on with this is the letters, as you move away from A to letters beyond in the alphabet, you're getting a more protective sample plan, right? It's higher lot size, and so it's more protective. They don't all have the same AQLs and LTPDs. The fact that it's indexed with something that says acceptance quality levels, AQLs, and percent non-conforming, they don't all have exactly the same AQL, right? And so it's really important, even though it tells you an AQL in this second row up here, that you actually evaluate the sample plan on an OC curve to find out precisely what is the AQL for my sample plan. Some of these sample plans have similar AQLs, but they're, as you go from top to bottom in these sample plans, they do have probably surprisingly different AQLs and LTPDs. Okay, another acceptance sampling plan that's very easy to find. It's on the FDA. You can go to the FDA website, and if you search for Quality Systems Inspection Technique or QSIT, you will come up with a couple tables that look like this. These are attribute plans where the sample size is given in the table and the acceptance number is in the header. So either accept on 0, 1, or 2. And then what's over here is this confidence limit and the upper confidence limit here. That's the upper confidence limit to a binomial confidence interval for the probability of acceptance. And so this number right here tells me that the LTPD for this plan is 70%. The LTPD for this plan down at the bottom is 5%. And so this sampling standard, you can use this to choose a sampling plan. It's wonderfully defendable because it comes from Quality Systems Inspection, but you still want to take, if I decide to use the sample size of 35 except on 0, I still want to run that through an OC curve to really see, then you'll be able to see exactly what's the AQL and exactly what is the LTPD. And you'll find that the LTPD is what is indicated with these numbers in this second column. Then there's also the 0 acceptance number plan. So all of these, you just get a sample size and then you accept on 0. You'll notice these sample sizes vary widely depending on lot size. And so just know that the plans towards the bottom of the chart have much more protection, meaning lower LTPDs, than the ones at the top. I will just point out that this sample size of 13 is a really popular plan. And so we're going to actually, evaluate that plan as our example. So, as I said, we want to kind of show you how to evaluate an OC curve plan for any, if you suddenly are the person kind of looking into an acceptance sampling plan, or suddenly you become the owner of a process and you want to know, is my acceptance sampling plan defendable? Does it have statistical rationale? The first thing you want to do is this OC curve calculation, and it won't take you very long. And so you can use a spreadsheet, and I'm given some references here for where you can get the formulas to do that spreadsheet. It turns out that the formula that we're going to use the most is actually programmed right into Google Sheets or into Excel. You can also use commercial software. Minitab gives these calculations. Sample Plan Analyzer is also commercial software that gives these calculations. Jump gives these calculations. There's probably more that I'm not familiar with, but all of these tools will give you these curves. So we're going to use the zero acceptance sample number. It's got an index, it's called an index value of 1, which is a good way to avoid calling 1.0 the AQL. It still sometimes gets called the AQL, even though it might not be the AQL, right? We're going to do these calculations to see what the AQL really is for this plan, but the sample plan is n equals 13, c equals 0. So I'm going to take a random sample of 13 units out of my lot. I'm going to inspect them, and I'm going to put them into either defective or non-defective. And if I get any defectives at all, then I'm going to reject this lot. And so we're going to use a spreadsheet first to make the binomial probability calculations. And then we're also going to show what it looks like to use software like Minitab. This tool is on the quality tools menu of the stat menu. So we'll get to see how both of those work. Now, the formula that we're going to use in our spreadsheet is shown here. This is from that NIST, from the NIST handbook, which I highly recommend that NIST handbook. If you're looking for a statistical, anything to do with statistics and you need to have a reference, the NIST handbook is a really good source. It turns out that Google Sheets and Excel have this binomial distribution formula programmed right in. So you don't have to worry about this formula here. You can just use the formula that's hardwired into the spreadsheet. And it allows us to do probability calculations with the binomial distribution. Remember, when we do attribute acceptance sampling, we're basing that on binomial calculations. So what does this look like? Here is a Google Sheet that I created for this particular purpose. You can actually just use, you could program this afternoon and have your OC tool. So what I need to know at the beginning is what is my sample size and what is my acceptance number. So I put those over here. And then I just literally create 2 columns and a graph. You wouldn't necessarily even need the graph. You really just need the columns. My first column is going to be a series of values of lot % defective. I happen to start at 1 and go, I probably went up to 50 or something like that, maybe up to 100. But you can start closer to 0, right? If you want more discrimination, and we'll kind of see that in another example. But in this case, I started at 1, and then I just have to program in what is the probability of acceptance. So this is my x-axis in column A, my y-axis is in column B, and then here's the formula, binom distribution, where I have to say my first value is my acceptance number. What is the probability of getting 0 defects? And then my next parameter here is my sample size. That's my 13. And then the probability of getting a single defective, that's the value in this first column divided by 100. And then I'm using true as a cumulative flag. It's going to accumulate the probabilities up to my C value. In this case, it doesn't actually matter to set it to true because it's only accumulating 1 number. And so then to find the AQL, we need to find out where is the probability of acceptance, 9.95. Now we see that at 1, it's already dropped all the way down to 0.87. So we know that our AQL is something less than 1%. Now, if you need to know the exact AQL, then you would have to expand. You'd have to have, 0.1, 0.2, 0.3, 0.4 in this column to really nail down what that AQL is. For my purposes, I just needed to know it's substantially less than 1%. Then I want to know what is my LTPD. Remember, I said that was the most important thing. So now I'm going to look at my probability of accept column, and I'm going to find where is that value about 0.10, right? 10%. And I find that that's, let's see. This must have moved on me a little bit because it's actually between It's actually here 0.10 and 0.08. That's where 0.10 is. So I've got this a little bit off. The LTPD is very close to 16% defective, right? It's right around in this value, but I probably grabbed the wrong two numbers because I'm trying to find 0.10 in this graph. And so I can report back just from this spreadsheet exercise that my LTPD is right around 16%. That means that values of percent defective that are less than 16%, I might actually ship those out, right? Values of, if I had an 8%, or let's find our favorite here. If I produced a lot that was 5% defective and I'm using this acceptance sampling plan, I'm basically flipping a coin whether I accept or reject that lot. And so it's really important to kind of look down this probability of acceptance line and kind of see what is the probability that you will ship that level of defective. Now, you can also do this in Minitab. You can do this in Jump, probably other commercial software as well that I haven't used. In Minitab, you will find it on the Quality Tools menu, Acceptance Sampling by Attributes. This is how you fill in the dialog box, and I'll go over this relatively quickly because I know not everybody uses Minitab. Two of the surprising things about using Minitab is that you don't have to fill in the AQL and the RQL, because of course that's what you're trying to calculate, and you don't need to fill in lot size. You can and see its effect, but you will see that the effect is very small. And this is how I put in my acceptance sampling plan, the sample size and the acceptance number. The important thing is that I'm going to click on my options button, and I want to add a whole bunch of additional quality levels so that I can get that table in more detail. So this time I actually put in 0.1, 0.2, 0.3, 0.4, 0.5, as well as the numbers starting with 1. So I'm going to look at it in a little bit more detail in this case. And so you just type those in, whatever other values you want to see. And then I'm going to get an output in Minitab that again has my percent defective column, just like I had in my spreadsheet. And then I have my probability of acceptance here. And so these are the same values. Now I can find out that my 0.95 level shows up right around 0.4% defective, right? That's not 40% defective, that's 0.4%. So less than 1%. That's my true AQL for this acceptance sampling plan. And my LTPD, again, is out here in the 15 to 20 range, meaning that it takes a defective level up around, 16, 15 to 16 in order to have high confidence that we will reject that lot. Minitab also gives us this graph, and so we can kind of see that 0.1 value is kind of hitting right around 16%. The 95% value is hitting here at 0.4%. Okay, so what we've done today, and luckily we've still got some time to talk about this. We've kind of talked about terminology, those 3 big misconceptions, and then how to really use acceptance sampling in the way that it is beneficial. A way to choose an acceptance sampling plan that has statistical rationale, that you can go into your audit being confident that you can defend the plan. And then we've seen how to use a simple spreadsheet program to come up with those calculations. Now, that spreadsheet program did not do the variables acceptance sampling, right? That's going to be a more complicated calculation. It can still be done with spreadsheets. It's just not simple enough that I can show it in a 1-hour webinar, but it can also be done with normal distribution calculations. So with that, I'd be really happy to take any questions.
Great, Karen. One of the questions is, are there any general guidelines to adjust the sampling plan based on having had multiple good lots or one or more bad lots in the past?
Yeah. So that's the switching systems. So those sampling standards do build in, if you get a whole bunch of good lots, then then sort of the risk calculation says that it's less risky of a process, so I can have less protection, right? But it's just a decision that less protection is okay because you've had some good performance, or in the other direction, we've had bad performance. So we want to increase our sample size. Those switching systems are built into the standards. What I recommend to folks is if you're using a switching system that, you know, with a lot of good lots, you go to a less protective, with a lot of bad, you go more protective. All of those sample plans can all be assessed for their AQL and RQL. So you can know how much risk you're adding by switching to the less protected plan. So I would, you know, there are those systems, they're absolutely in the sampling standards. They're, you know, they can, you know, all of this is good fit to your situation. Do they provide the level of protection at the right cost for your product? But I'd encourage you in those systems as well to just run the OC curves for all the possible sampling plans you might use. And then you'll really know the impact of switching to a different sample plan.
Great. Where do you find all the standards?
Oh, yeah, that's a tricky thing, isn't it? So ASQ sells standards, right? So they are book, you know, the real standard, you can either get it electronically or in a book, and it's got the actual form. When I was at Medtronic, we had a subscription service to the standards. And so through your company, you know, find out from your, whatever your corporate information folks, information management folks are, you know, used to be called the library, find those folks and find out how you access standards, because it's really important to have a real current version of the sampling standards if you're using them. Now, you know, it's absolutely true that you can Google these names and sometimes find an old version, sometimes find an illustration online. But you know, if you're really investing in this technology, it's really great to be using the actual standard and to know that you're using the current one. So they are, and sometimes book there's a book for the Accept on Zero plans. That's a topic for another webinar. Actually, the Accept on Zero sampling plan book, if you Google that actually, or go to Amazon and type in zero acceptance number, you'll find the book with the author. His name is on the slide, I think, where I talked about that, Nicholas Squiglia. The most current version of that book actually has two different tables. There's sort of the classic and the new version of that table where the numbers change just a little bit. There was one version, one edition of that where the table changed a little bit and it wasn't obvious how it had changed. And so the newer versions show the old and the new version. The sample sizes don't change very much, but they change just enough. So if you ever have trouble with that zero acceptance number book, check and see what version you have, and sometimes that can explain it.
For high-risk products, such as class 3, do you have what a typical risk level for LTPD might be?
Ooh,
I know that's kind of hard to say, but
right. It's a hard question. It's a good question and a hard question, because you know, I mean, you'd like those LTPDs to be like 1%, right? You'd really like to push them as low as you can stand. You know, for the, you know, you want to think about acceptance sampling as one of the tools that assures quality, right? And so typically, as much as I would love to have an LTPD of, you know, 0.5% or 1% or 2%, those plans are pretty expensive, right? Because we saw that sample size, you know, if we go all the way back to up to my Accept on Zero OC curves, you know, if we have a sample size of 120 Accept on Zero, we find out that the LTPD is sitting here, you know, sort of in right about 2%. Right. So to get an LTPD that's even lower than 2% is going to be a sample size in attribute sampling of more than 120. Often, you know, our lot size is 100, right? So we can't destroy, and sometimes this is destructive testing. And so LTPDs, while they're never as satisfying as we'd like them to be, we at least need to know what they are, right? If the LTPD is 50%, you sure want to know that. You want to know that my lot has to get all the way to half good, half bad before I have a chance of detecting it. That's the LTPD for sample sizes of, single digit sample sizes. And so I guess, high risk product, you want to have LTPDs that are as low as you can afford. And then you usually have to be satisfied with LTPDs that are higher than you'd like them to be. And then the other thing that leads us to do is to make sure that just doesn't happen very much, right? If you never produce, 10% bad product, because you have proactive measures in place to prevent that, right? You've got your DMAIC projects, you've got your good process control and monitoring, you do all the right things in your process, then this is just your acceptance sampling plan is just an insurance policy against something that's a huge surprise, right? Your supplier made a change that they didn't realize impacted your product. They're working in good faith. They didn't tell you about that change because they didn't think it mattered, and it turned out it mattered, and suddenly you've got 15% bad product and you had no idea this was coming. That's what acceptance sampling is good for. It's not good for keeping quality nearly perfect all the time. We need DMAIC and process monitoring for that. I sound like an evangelist, don't I? It's this weird thing. I actually was taught about acceptance sampling when I was in grad school a long time ago. And I basically then said, well, that sounds like a bad thing because it's not proactive. And I proceeded, to think I would never need to use it. And then I found myself in the medical device industry, and I suddenly needed to communicate on these topics. And so I ended up learning that, yes, that was true what I learned before. It's not good for process improvement, for keeping high quality, but it is good as this insurance policy, because every now and then we don't know what we don't know, right? We don't even realize that we're at risk of a change. And then this change happens and we want to be able to react to it very quickly. That's what acceptance sampling is really good at, is guarding against the things we don't see coming.
Great. Well, I think we're about out of time. So that was a wonderful presentation. I did tell everyone in the chat that I'll be sending a link to the slides and the recording. It'll be up on our YouTube channel. So you'll be able to watch this again if you want to watch Karen give this presentation over and over again into, perpetuity.
Right. Hopefully that helps.
Okay. Thank you so much. Everyone have a good day.
Very welcome. Thanks for coming, everybody. Have a good day.